10:08. 4:68.
That's supposed to be a 1.
10:06.
Just check those. Did I write those correctly? Good. Okay, good. Good morning, people. Congratulations on getting up. And these things cannot be easy, are often not easy, especially in a beautiful place like this. I'm running on jet lag, so I'm good. So I have decided, unilaterally, without consultation, that I'm not going to finish talking about the brittleness of what we did yesterday. So remember we wrote all those assumptions yesterday, and I said the method's very brittle, in the sense that as we change those assumptions, lots of things become harder or different or more difficult or impossible. The reason I'm not going to finish is I wrote most of what I would say in this archive contribution, which is called Fitting a Model to Data, which I wrote with two of my former students. And this is a 55-page document about fitting a straight line. And there's one substantial error in the document, and your mission, if you choose to accept it, is to find the error. Yeah, the 10:08. There's a substantial error, which we need to fix, but we just haven't. We've got it basically ready. We just haven't fixed it yet. Actually, you can find it by going to the GitHub repository and looking through the issues. So that's the cheating way to find what's wrong with that paper. This talks about it. The first few sections of this paper are about the magic that we did yesterday, about the magic that linear algebra solves all your problems and gives you a Cramer-Rao optimal estimator for that problem. So the first few sections are about that. And then it goes on to talk about what happens if you have outliers, what happens if there's an intrinsic width to the distribution, what happens if your model is nonlinear, what happens if you want to put priors on the problem, and so on. This also is filled with exercises. So if you want to work on the real basics of inference, there's a set of exercises in there that do exercise basic inference. Most people are interested in more advanced topics, but if you do want to strengthen your fundamentals. There's an even more elementary paper I wrote, which I haven't put up here. I don't know its archive number offhand, but it's something like probability calculus for inference. It's called something like that, probability calculus for inference. And that is really basic, just about what kinds of manipulations are you allowed to do on probability distributions, which is useful for debugging, or debugging your thinking process rather than your code. If you're having trouble writing a probability expression or something's getting confusing, this probability calculus for inference is just the basic rules, and you can kind of audit your thinking around those rules. I don't. Can somebody pull it up? Oh, I do want you to give it to me. Just a sec. That's correct? Did I write that correctly? You see, archive went to 5-digit past month. By the way, I'm a huge believer in archive, as you can imagine, and from things I said yesterday, and I have a paper on archive from its first year of existence. And it's fun to look at those early papers because that's when the internet couldn't handle images. So the papers, all the figures say, figures available upon request. It's hard to believe how far the internet's gone. We're streaming video, HD, whenever we want it. Okay, good. Today, I'm going to talk about MCMC, and we're going to start by where we left off yesterday. But instead of doing the detour into the brittleness of the method, I'm leaving that for this document here. It's 60 wonderful pages, or 55, I think. This is also an immensely long paper, 1710, where I and a former student, Dan Foreman-Mackey, talk about how you use MCMC. What is MCMC and how you use it? Dan Foreman-Mackey is the author of the MCMC package MC, which some of you might know if you have some connection to astrophysics. It's widely used in astrophysics. But anyway, we wrote a kind of user's manual for MCMC here. And that user's manual, and it's also fairly conceptual. It's designed to find thinkos in your work. It's also designed to help you assure yourself that what you've done is correct.
Can you define thinko, please?
Thinko, it's like a typo, but it's in your brain.
Oh, okay.
There's also conceptualos, which is a cereal that you eat. What I'll say today, I'll just hit some highlights. I can't say obviously last time we learned I couldn't say everything in this paper. I couldn't even say a quarter of it. And similarly, I won't be able to say everything in this paper. So if you're interested in MCMC, I recommend this. Also, if you think there's advice or problems you have with MCMC that are not in this paper, we're interested to hear about it because this really is supposed to be a really useful thing where if you're going to do MCMC, you can breeze through this and it will give you a sense of what things you should be thinking about. It's supposed to be written in a kind of user's manual style. Oddly, so this also contains exercises. So if you want to get going on MCMC, this has exercises in it. And some of the things I'll point you as I talk today to some exercises you could do. Those exercises are fun and easy. You'll learn a lot by doing them. And I had something else to say about that, but it's gone. Anyway. Oh yeah, the APJ, the Astrophysical Journal, has just published this article with the exercises. So we believe we have the first publication in the Astrophysical Journal with exercises in it. I also have the distinction of having the first article in the Astronomical Journal that contains a photograph of a kitten, which you can also try to look up. The title has the word astrophotographers in it. Okay, good. Yeah, hit me.
Dive into things. What is your preferred coding language for data analysis and why?
Good question. So question, what is my preferred computer language for data analysis and why? That's a good question. My answer is I'm very, very neutral on computer languages. I think it's very context dependent, and most people are working in environments where there's a lot of pre-existing code. So in astronomy, right now in astronomy, the pre-existing code is all in Python 3. So we recommend people work in Python 3 if they just want to get started fast. But in different contexts, it's different. In particle physics, people use root. And so you need to work with languages that interface well with root. In much of the stats community, people work with R, which is very built out in stats. So almost every important method in stats has a reference implementation in R. There are also like probabilistic languages like Stan that are designed for probabilistic models, which are useful if your model fits into certain model classes. So I think it's very context dependent. And half of the context is what field am I in, and half of the context is what problem do I need to solve. So I think there's no simple answer, unfortunately. But the nice thing is in astronomy, there's been a lot of consensus around Python 3. And so most people are using some mixture of Python 3 and C++ in astronomy. So that's been good for me because I can't actually handle that much load when it comes to languages. But you know, Dan Foreman-Maggie, who co-authored this, I mean, parts of his code base are in Fortran, parts are in C++, parts are in Python. We touch other languages occasionally. R we touch. Java, JavaScript, all sorts of things come in at different times in our problems. Good. Shall I? Okay, so today's topic is MCMC, Markov chain Monte Carlo. Markov chain Monte Carlo methods this is one of the many data analysis things that were invented, at least in part, by physicists. And a lot of people involved, and a lot of the names associated with MCMC are physicists. I'm not going to talk about the history of it at all. I'm just going to jump straight into how you use it. There's a lot of nice writing on the web about the history, and it's complicated. The methods are named after the wrong people and all sorts of things, all the usual fun things. And I'm just going to use common names for things, but don't treat those as endorsements of the history. Actually, I think in physics we should get away from naming things after people, because it always turns out to be wrong in the end. They should be the equations of electromagnetism, not Maxwell's equations. They should be the equations of general relativity, not Einstein's equations. And we should call this, this Markov property is named after a person. But anyway, yes, I do. Monte Carlo, it's a lovely place to visit, but it really has nothing to do with this. But at least it's neutral territory. Okay, so let's see. There's many different ways to come at this. There's this beautiful concept of what is Markov symmetry and things like that. I'm not going to talk about any of that. I'm not going to talk about the math of this really. I'm going to talk about the statistics and the data analysis use of it. So let me, before we get here, let's just go a little further in the problem we had last time. So remember last time we had a problem where we were able to write down a probability for our data object given parameters and some assumptions and housekeeping data. So there's assumptions and housekeeping data, and then there were parameters we care about, and then there were our data, which were these measurements. And in the case that this probability distribution was Gaussian and the model was linear in these parameters, we got this beautiful solution. As somebody pointed out, only a tiny fraction of all models fall into that class. And that's absolutely true. In fact, essentially no models of interest in my group fall into this class. And I don't do nearly as hard problems as things like the Higgs mass. So we're talking about, so one thing that happens is these parameters affect the model predictions nonlinearly. So you now don't have a convex operation to find the best fit. There might be multiple modes. In fact, in general, in problems, there are multiple widely separated modes that are all reasonable fits to the data. That happens very generally. Also, often you have additional information about these coming from other sources, these parameters from other sources that you might want to add, or constraints on these that you want to add, so you can't just give them arbitrary scope. And often when your problems produce some uncertainty in these, you want to kind of propagate that uncertainty, and so on. So there's a lot of things that we kind of weren't able to deal with, or it's not exactly that we weren't able to deal with them in the way we were thinking about it last time, it's that they would have made things a lot harder. So in general, so now what I'm going to do basically is talk about how we would approach this problem in the general case, when this is a general function where we don't have any nice properties. What do we do then? And the second thing I'm going to do is I'm going to move to a Bayesian perspective. So I'm going to take now a Bayesian approach to this problem. I'm going to think about it like a Bayesian, and we're going to work through how you solve this problem as a Bayesian. Now, I'm not going to talk in too much detail about like Bayes' theorem and things like that. I want to get quickly to how we actually operate on the system, and that's where MCMC is going to come in. MCMC basically is only useful to you if you're a Bayesian. It is true that you sometimes have situations where you might want to sample some probabilistic distribution using MCMC in other contexts that aren't about inference. Like if you were doing a particle simulation, you could use MCMC to do a simulation of your experiment. But if you're using it for inference, you are doing something Bayesian. And sometimes people, I encounter frequentists using MCMC, and usually they are making some kind of mistake. Now, in the Bayesian context, we have to add something. We have our likelihood function here. We also have to have a prior over the parameters in the Bayesian case. So in addition to this, which we call the likelihood function, we also need something which we call the prior, which is your prior probability, the probabilities you would have put onto these parameters before you got your data. And this is an additional assumption. Remember, an enormous number of assumptions went into this function. So I want to be just careful here. Remember, I was talking about subjectivity. An enormous number of assumptions went into this function. We assumed a form for the model. We assumed things about the noise. We assumed things about the data points, and so on. If you want to be Bayesian, you still have to make yet one more assumption, which is you have to write down a probability over these parameters in advance of your data. And this has two aspects to it. One is it should encode your beliefs about those parameters before. So for instance, sometimes you know that some parameter can't be negative. Sometimes you know that a previous experiment measured the parameter and got some value and you basically believe that experiment. Sometimes you believe that certain combinations of these parameters would violate the null energy condition, or something like that. You often have various kinds of beliefs. Some of them might be rooted in physics, like your physics knowledge or symmetries or things like that, and other things might be rooted in prior experiments where similar measurements or related measurements have been made. So that's one aspect of the prior, that it should encode somehow your beliefs. This is called the prior. And if you're a true subjective Bayesian, you would say it really should encode your actual beliefs. But there's a second thing the prior brings you, which frequentists do not have, which is that it brings you a measure in the parameter space. What do I mean by that? I mean the following thing. The integral of p of theta d theta is 1. Meaning if you integrate this function over the parameter space, you get unity. That is an integral that no frequentist can do. That's the rules. This is the statistical philosophy difference. In frequentism, you cannot do integrals over parameters. In Bayes, you can. So Bayesians have more capability than frequentists, but it came at the cost of an additional assumption. You had to assume something else, but you got new capabilities. And that's what today's lecture is going to be all about. Yeah?
So I'm sorry, I don't think I understand. Why is it that a frequentist can't sum all probabilities to 1 effectively?
A frequentist can, but they only have probabilities over data. They never have probabilities over parameters. So the frequentists can integrate this, dy, and get 1, but cannot integrate d theta, ever. You just can't do this. Because for a frequentist, this is a unallowable assumption that there's a way to parameterize, that you can put a metric, basically. It's about whether you, not a metric, a measure, whether you can put a measure on the parameter space. That is an unacceptable additional assumption for a philosophical frequentist. But as I said, I'm a pragmatist. Sometimes this is a really important and valuable thing to be able to do. When I need this, we're Bayesian. When I don't need this, we're not. Yeah?
So if you're assuming that some parameters should be positive, how should you integrate that to get 1?
This, I didn't say what domain the integral is over. So this is like over all theta. I'm being unambiguous because theta might have integers in it. It might have continuous parameters. It might have vectors. It might have tensors, all sorts of things. So there's some domain of theta. And the idea is that either you limit the integral to the allowed domain of theta, or this function is exactly 0 where theta isn't allowed. See, there's a kind of support concept. This probability distribution has support only where theta is allowed. That's another way to think about it.
Would you calculate the same, the one in the prior and the likelihood function of those?
Ah,
The same?
good. Great question. The question is this I the same as this I? In my view, yes, because what happens when we became Bayesian, we added additional assumptions to I, which permitted us to write this down. But yes, I for me is just this catch-all that's taking all the assumptions that I don't want to write down over and over again.
We actually have to calculate the form of that probability density.
We're about to talk about that.
Gives us some constraints.
Good. We're about to talk about that, exactly what you do need to calculate. So the nice thing about MCMC, and the reason MCMC is such an important and powerful tool, is it limits the number of things you have to be able to calculate. For instance, we'll never have to actually do this integral. And we'll see. Yes? If you have absolutely no idea what theta should be, and you have no willingness to kind of write down a space or say what thetas are close to each other or how close they are to each other or any of those things, then you can't be a Bayesian. Not permitted. And that's one of the reasons that many people are philosophically frequentist. And that is a perfectly reasonable thing to do. My view is that our job is to deliver good results, so we shouldn't get caught up in philosophy. We should work on things that will give us good results. But there are philosophical issues which do matter. And as you noticed last class, I was encouraging us to be pedantic. Somebody over here? Yeah, go ahead.
Like, what's the problem with having a flat prior then? Do you know anything about that?
Well, if it's flat at all theta, this can't be true. If to be a proper Bayesian, you need to specify this thing. There are some edge cases where you can have an ill-specified prior still successfully develop a posterior, but that's a kind of edge case that I don't really want to talk about. We should either be fully frequentist or fully Bayesian and not try to skate that boundary. Yeah?
Can you give an example of any sort of parameter that people would not want to put would feel uncomfortable putting any sort of prior on? Like, is there anything where they wouldn't have a good guess?
Yeah, that's a great question. The question is are there parameters on which no one would ever have any idea? I rarely encounter such parameters, but there are some true nuisance parameters in things we do. Like, we have problems where we modeling outliers, and we just really don't know what the rate of cosmic rays is as a function of time or whatever, and the rate could be anything, really anything. Now, of course, that's not really true that it could be anything, because actually we've launched lots of satellites and we know how many times cosmic rays have hit their CCDs. So usually when we say, oh, I have no idea, we're just being lazy, because you could just look at some data you've seen before and you would have a reasonable idea. So I think in most cases it is possible to write down priors, but one of the issues with priors, which was kind of implicitly in your question, is that if I reparameterize theta, to another parameterization, there'll be some Jacobian factors that come into this thing which change the form of this. And so if you had flat priors in one parameterization, they won't be flat in the other parameterization. And so that's why, in general, I'm kind of against the idea of just putting something generic here. I think you really should think about what really do you know about it and put them in. That's my kind of feeling. That's why I'm sort of a subjective Bayesian. Yeah?
Actually, just one example where we don't know if in physics is calculate a cross-section for given order perturbation theory, right? Mm-hmm. What's the uncertainty on that? What's the distribution? This is the example where...
Yeah, that's right. Good. The comment is that there are times where you have like an expansion for a cross-section and you truncate that expansion somewhere and you really don't know what the magnitude of the next term in the expansion will be. That's a very nice idea, and that would be one. On the other hand, you've done a lot of such calculations, so you still could at least say, you could still keep support at all values, because this is a pretty weak, the fact that this has to integrate to 1 is pretty weak. You can still have support at all values of theta. For instance, unbelievably wide Gaussians, for instance, have the property that they have support at all thetas, and you probably don't think the next order is 10 to the 80 times larger than the previous order. So it's not like you have none, but you do. But I agree, there are places where you're pretty damn uncertain. One of the nice things is often your data. I mean, one of the reasons why people worry too much about this, and there's two sort of general philosophical comments about this that I like to make. One is far more assumptions go in here than here. So though you should worry about the assumptions here, I'm not telling you not to, you should worry about them in proportion to what fraction of all your assumptions they are. And I think in most problems I work on, this is like 5% of our assumptions, and this is 95% of our assumptions. That's one thing. The other thing is, in most cases that you will work on in your life, the data will be informative enough that your choices here won't actually matter that much. Almost all problems I work on are completely likelihood dominated. So as we modify the priors, nothing really changes about our results. And in fact, when we modify our priors and our answers do change, we usually say in the abstract, we don't really have a result. We don't say, here's our result, suck it. We say, it's very prior dependent, but it looks like there may be an effect there. Yes?
I was going to say, isn't part of the power actually also that even if you can't constrain the prior a priori very well, you can look at the posterior distributions and from that inform what your next guess incrementally happens.
Good. The question is about isn't the power that even if you don't know your prior very well, or don't have a well-specified prior, once you've done an experiment and got a posterior out of your first experiment, you can use that as a prior for your next experiment. And that's a beautiful thing. There's a whole beautiful philosophy of Bayesian reasoning, which is that each new experiment updates your beliefs, and your beliefs for your next experiment, your prior beliefs for your next experiment, or your posterior beliefs from your previous experiment, you see? And there's a daisy chain of reasoning. And there's a whole consistent theory of reasoning that Bayesianism is based on. And it's also the reasoning that is the basis of the insurance industry. In fact, Bayesianism was basically created by the insurance industry. And the insurance industry is very old, and insurance is a form of betting. So Bayesianism is kind of the language, is the technology behind betting, bookmaking, and insurance. And bettors, bookmakers, and insurers have made a lot of progress in Bayesian reasoning because it is about predicting the odds for outcomes given all the information you have. And it's a consistent story for reasoning about unknown outcomes. Yeah.
If you were to go down that path, you do the experiment, you take your prior from that, could you fall down a rabbit hole of going to a false minimum by meaning if you have an odd result your first time and you don't see the true minimum of the false minimum, you keep on using that prior, you would narrow down into...
Good. The question was about whether this daisy chain of going from prior to posterior to as the prior for the next to posterior takes you down some rabbit hole where you get stuck in a local minimum. The answer is it will if your model doesn't have enough generality to begin with. So if you choose overly restrictive assumptions for your likelihood function or for your prior, but the more dangerous thing is your likelihood function may end up peaking up on the wrong answer. Because there might be, if you use some more flexible noise model here, other answers would become available, which other experiments would support. So there is a problem of daisy chaining everything together like that. But of course, the daisy chain doesn't have to literally be time ordered. You can go back at the end of the last experiment and then reconsider and rerun your reasoning right through the whole chain again. You're always allowed to redo it. In fact, one of the points of consistency of Bayesian reasoning is at the end of the day, it doesn't matter even what order you considered the experiments. You can reorder them and you'll still get to the same posterior at the end. That's one of the conditions. Actually, Bayesian inference flows from a few very simple principles. It's a very beautiful thing. And if you want to look at those principles, the best book is this book by Jaynes, called something like Probability, the Logic of Science, or something like that. But this book, the first few chapters of this book, takes you through the very simple and beautiful argument that Bayesian reasoning is a consistent way of reasoning. So it is true that Bayesianism involves one additional assumption over frequentism, but it gets you a lot of power. It gets you the power to do certain kinds of integrals, and we're going to show what those integrals look like in a second and how valuable they are. And then it also has this kind of consistency. Now, there's a lot of debate in the statistics world about whether there's any truly consistent statistical philosophy, and I'm not going to get into that. But there is some beauty to these arguments. Jaynes, by the way, credits a statistician named Cox for this reasoning, but I think it might be even older than Cox. Okay, good. Yes?
If you know that an energy density, for example, being negative is non-physical,
Yeah.
and you're trying to do something frequentist, is there any way that you can save computational energy, whatever? Is there any way, without using the Bayesian priors,
Good.
you could do frequentism with, and I know that this equation is not a physical.
Yes, you can. So the question is like, can you put beliefs, strong physical beliefs, into frequentist analyses too? And the answer is yes. It's not exactly, a lot of Bayesians will say that there are things that frequentists, I just said there are things frequentists can't do, but they're technical things like this. In fact, most things like propagating uncertainty, I'm going to show you propagation of uncertainties, how beautiful it is in Bayesianism, but it is also possible to propagate them perfectly well in frequentism. Similarly, it's possible to put constraints. You can also reparameterize to parameterizations that don't touch unphysical regions. There's lots of ways you can put in constraints and so on in both frequentism and Bayes. So that is not a constraint. And of course, many particle experiments over the history of particle have been frequentist, and they are able to put in all of their relevant knowledge. So it's not so much, it's the question of whether the knowledge goes in here or whether some of it goes in here. For frequentist, it all goes in here, and for Bayesian, a little bit of it goes in there. Okay, good. Now, let me just remind you that the way Bayesian inference works is that you start with prior beliefs about these parameters theta, and you're going to end with posterior beliefs, which is you started with beliefs about theta, you're going to end with beliefs about theta, but now your beliefs about theta are not going to be just conditioned on your assumptions, they're also going to be conditioned on your data. So you started with this, and you ended with this. And if your data were informative, this should be a much narrower distribution, or a much more informative distribution than this. And that's kind of the principle behind Bayesian inference. And Bayes' theorem is that this thing is just some normalization factor times p of theta given I, p of y given theta and I. This posterior is constructed by multiplying the prior by the likelihood and renormalizing it so that once again it integrates to 1. See? That's the Bayesian step. You multiply the prior by the likelihood, renormalize. And that's not how all Bayesians write that, but I write it this way for a very, very specific reason. Some people would write this z as a probability also, but I do not, because I, in my working life, try to never compute that object z. It would be a probability of the data given your assumptions.
Which is different from the py theta I?
Yes, because there's no theta in it. It's integrated out, which is hard to do. So what I'm just about to write that. Computing z is, in general, hard/impossible. And almost all true Bayesians would disagree strongly with that statement. But they're wrong. I have almost never seen a computation of this prefactor, this factor here, that is believable in astrophysics. The only ones that have been done in astrophysics that are believable are in tiny little problems that are trivial. In any real problem where you have tens of parameters, then you're talking about an integral in tens of dimensions with an unbelievably non-trivial structure on those tens of dimensions. And no one can do integrals like that.
So then how do you normalize?
We are going to avoid it. So the beautiful thing about MCMC is it permits us to understand the posterior of the function and do integrals over the posterior of the function without ever knowing z. And in fact, that is the only point of MCMC. And so most people think that MCMC is this critical thing for inference. The only point of MCMC is to avoid computing z. That is it. And some of you have heard, there are methods, MCMC methods, which I'll mention later, that are designed to allow you to compute z, but I think that's like missing the whole point. I have various statistics collaborators who would agree or would disagree very strongly with that. But we are going to now avoid ever computing z. But let me just take a little aside before we get there. So this is my introduction. That's Bayesian inference. That's everything you need to know about Bayesian inference. Now we're going to step aside and talk about what a sampling is for a minute, and then we're going to talk about how MCMC gets you that sampling. So let me move to a new board. So what is And I could even say, what is a good sampling? Okay, so what is a sampling? So in Bayesian, as I said, Bayesian inference allows you to do integrals over the parameter space. And in fact, it turns out that everything we're interested in Bayes is an integral over the parameter space. So for instance, if you take some data and you want to predict what the next data point will look like, what you do is you get the posterior on your parameters, and then you make your prediction for the next data point integrating over the parameters. So you consider all possible values of the parameters that were consistent with the previous data, and you use them all to predict your next data point. That would be a marginalized prediction. So you do an integral to predict your next data point. Or if you're asking, what's the mean of my posterior? If I want to know, like if you just want to write a number in the abstract for the mass of the Higgs, what number are you going to write down? You can't write a probabilistic distribution over abstracts, as we discussed yesterday. So you have to choose a number. What number do you choose? Well, you might choose the mean of the posterior. Well, guess how you get that? By doing an integral over the parameter space. Or you might choose the median of the posterior, which you also get by doing integrals over the parameter space. So you're always trying to do integrals over the parameter space. You're doing integrals that look like this. Some function of the parameters times p of the parameters given y comma I, meaning this is some random function. This is my posterior. And I'm integrating over the parameter space, over the whole parameter space. And this gives me, or even some subpart of the parameter space. If I'm doing a histogram and I want to measure in bins, things, I might do integrals over little pieces of the parameter space. But whatever, I'm doing integrals over domains of this probability weighting, basically weighting whatever function by this probability and integrating over the space. These integrals are basically the whole language of Bayesian inference, and all of Bayesian outputs are in the form of these integrals. And a sampling is, I can replace this integral with a sum over k samples, k equals 1 to capital K, of f of theta k. It's an approximation. This integral can be replaced by this sum. See when that would work? See how this would work? This will work if these thetas theta k's, are drawn fairly from this distribution, then the integral over this distribution will look very like the sum over a set of fair samples. That is, by the way, the definition of a sampling. That's the definition, and the definition of a good sampling is that this is a good approximation to that, and if you want to go all mathy, there's epsilon delta things you could say. Yes? Quantitatively, it's about how accurately this approximates that. You don't, and we're going to come back to that. You never know. Yeah. Yes?
Is that approximation exact as k goes to infinity?
Yes. If this sampling is fair, as k goes to infinity, you get exact. Yes, that's correct. Unfortunately, it approaches it very poorly because this is stochastic. So you generally get root n. And the root n can have a terrible prefactor because you can have, your posterior can look like this, and this can dominate the integral but rarely appear in the sampling. See? So not only is it only stochastic convergence, but it can be stochastic convergence with a terrible prefactor. Yes? Oops, sorry, I meant to do 1 over k. Thank you. That's an error on the board. How did it take so long? Thank you. It's an average over the samples. Thank you.
Can you define stochastic approach?
All I mean is you get like root n. Okay. So you only get root n improvement. So if you want twice as good an estimate, you have to do 4 times as many samples. So it's bad convergence.
To be fair, because that's integral on F, like the probability distribution, we should take more samples from the regions
Where F has support. The point is that you could do a better job. You could, if your only purpose of your sampling was to estimate this integral and no other integrals, you can sometimes do a better sampling than a fair sampling. There'll be non-fair samplings that are better. But that is very, very specialized. That not a place you should go unless you really need to, because there's a lot of ways that can go horribly wrong. But for instance, if you know this thing has very finite support, then you can cut P of theta at the support and then do MCMC just like we're going to do it, but with this cut P of theta, and you'll get a much better sampling. Yeah.
From cutting your priors more precisely?
You could also have done it by cutting your priors at the same place. Yeah, that's right. So if you know a lot about what functions you're going to need to integrate later, you might want to modify your priors to not bother inferring in places where these functions have no support. But most functions that you're using here don't have those simple properties. But that is a very good point. One of the things we have to remember is, well, anyway, we'll see. We'll see how this looks at MCMC when we do MCMC. Yeah.
Is that a measure of probability sampling if it's true for all of them?
Good question. The question is, does this have to be true for all F? There's no sampling you can write down that's true for all F. Because I can make F a delta function, and no sample will ever hit it. So there's no way you can make this true for all F. So a sampling, whether your sampling is good, is guess what? Subjective. Because it's about what kinds of functions you're going to do your integrals of. And if you're doing functions that are very, very featured, you're going to need better samplings than if you're doing functions that are very smooth. If all you want is the mean of the posterior, you don't need a very good sampling. But if what you're trying to find is some probability that the model is in some tiny fraction of your space, you are going to need an incredibly good sampling to see it. Good. Yeah, it's F dependent. This question of whether your sampling is good is F dependent. That will come back up if I don't run out of time, as I'm predicted to do. Shall we? Okay, good. So MCMC is a tool for generating this sampling. So what MCMC does is it generates the sampling. The input is any function proportional to this. I don't need to know Z. I don't even need my prior to be properly normalized. This doesn't have to integrate to 1. It could integrate to 17. All I need is a function, a callable function that is proportional to this. Meaning, if I move in theta, as I move around theta, I'll get bigger and smaller values of this, but I don't actually need this function to integrate correctly. Or another way to say it is I don't need to know Z. I could just put this product in. So what I need is F, I've already used F. So some G, let's call it Q of theta, which is proportional to P of theta given, let me just write it fully out. All I need is a function Q of theta that's proportional to this. And if I have that function, I can generate a fair sampling from the properly normalized probability distribution. And that's what MCMC does. Good? And the reason that we love this is the reason that I wrote on the board right there. Calculating this normalization is often impossible, and so I need a method to get a sampling without computing that integral. Otherwise, I'll spend all my time computing that integral, Of course, if you can compute that integral, you can also integrate lots of other things, and so integration isn't hard for you. So then do those integrals. So if you're in a situation where you can compute the integral and you're confident, just compute the integral. In that sense, MCMC is a method of last resort, because it's the method you use when you can't do integrals. Now, of course, most people use it anyway, even when they aren't in the last resort state. And that's partly because MCMC is so beautiful and so simple and so well implemented that it's just whatever. And you can write your own MCMC code in about 10 minutes. The code looks like this. It's a Markov chain. What does it mean that it's a Markov chain? It means that we have a state at one time, and we're going to update to a new state using only the properties of the current state. So that's the sense in which it's Markov. And so the algorithm is this. At time t, I have parameters theta t. And then what I do is I choose, by a random walk, for instance, I choose a new set of parameters, theta prime, from some proposal distribution. Now I'm overusing variables. Let's call my proposal distribution, I'll call it capital Q. Capital Q of theta prime given theta t. So I have, at time t, I have parameters theta t. Now what I do is I choose a new set of parameters from some probability distribution. We'll call this the proposal distribution. Why am I calling it the proposal distribution? Because this is a distribution that makes proposals for new parameters that I might consider. Okay. Then what I do is I select a random number from uniform of 1, meaning the uniform distribution from 0 to 1. Everyone still with me? Then, if, now is the place where I have to get my greater than or less than sign correct. Here we go. Q, there's little q, of theta prime over Q of theta t is greater than R. Theta t plus 1 equals, actually I'm going to even draw it like this, gets assigned to theta prime, gets assigned to the value of theta prime, else complete MCMC method. It's absurd. Yes, ask. This is acceptance. This step is called the acceptance rejection step. So this is the proposal step. So you have your state. You make a proposal. Importantly, the proposal depends only on the current state, because that's what makes it Markov. And then this is the accept reject step, where you select a random number and you either accept it if you've either gotten better, because this can only be one, so you've either gotten better, you accept it, or if it's gotten worse, you accept it sometimes. And if you don't accept it, you literally duplicate your current value. Yes?
What does a computer do if the ratio is equal to R?
It literally does not matter whether you make that less than or equal to or less than.
The computer's just not going to care?
Yeah, it only happens 1 in every something like 10 to the 6, 2 to the, I don't remember. It happens very rarely, so it doesn't matter, yes.
Is the proportional distribution is also part of your assumptions? Or
The funny thing is, on very weak assumptions, this method is guaranteed to produce a fair sampling in the limit of infinite time. So as long as you run this for infinite time, it doesn't matter what you choose. Now, I've never run this for infinite time, so I've had to use, so it is true, as you're identifying, all of the art is in choosing your proposal distribution. Everything is about the proposal distribution. And if you choose it badly, you do badly. And if you choose it well, you do well. That's what it's all about. I'm about to talk about that. Yes, keep going. Which
So
are?
now we should put a measure in place to decide when you're good and stop doing that.
Exactly. We're about to talk about when you're done. That's what I'm about to talk about. Because, of course, what you do is you run this for a while, and sometimes if your proposal distribution is really bad, this gets rejected every time. You can easily run this for 20,000 steps and have 20,000 duplicates of the first number you started with. I've done that many times. Other times, you can have it set this wrong, and it'll move or it'll random walk around, but you know your distribution looks like this, and it's spent all 20,000 steps right here. Like there's all sorts of things that can go wrong here, but when you tune this correctly, this does pretty efficiently get you samples from your posterior and fair ones. Yeah. Q is a function that is proportional to this product. In fact, we do this, when we really do this, I've kind of lied here. We actually we do this, we always use log probabilities, and this is log, remember? We do log, and this would be a sum, and this would be log Q, and we'd ask whether log Q minus log Q is greater than log R. We do everything in logs, of course, for dynamic range issues, yeah. I don't know. It does have some other names, but I don't know. And there, by the way, I have made an additional assumption here. The actual algorithm is slightly more complicated than this. This is actually a slightly wrong statement of the algorithm. This form of the algorithm is only true if Q of theta prime given theta t equals Q of theta t given theta prime. Yes, if you make this not true, then there's a factor of capital Q's that comes in here as well. But we actually advise people to stick with this form. This form is still very generic. Gaussian, where this is the draw and this is the mean, has that property. Gaussian, you can swap the mean and the draw. Mixture of Gaussians is still good. Various kinds of uniforms and things you can set up have these properties. Yes? Say that one more time. Yeah. Good. The question is like, aren't there times where you can never kind of walk from one part of the probability distribution to another? In principle, if you construct this cleverly, you can ensure that you always can walk to any other place. But in practice, you're right. Often we have, actually I encounter this problem a lot. When we do binary stars, we have a few measurements of the star, and there's different, very qualitatively different orbits that could fit the data. And there's really no way the MCMC method can walk from this solution over to this solution, which have totally different periods, totally different phases, everything's different. So there's just no way it can walk from here to here. And we have to build special purpose samplers for those problems. So this really is kind of this gets hard. So when does this work well or work badly? This works badly if three big times it works badly. One is if your proposal distribution, Q of theta prime given theta t, is too wide. Meaning, if every time you propose, your posterior is here, and you propose, okay, I'm going to jump here. No, that didn't work. I'm going to jump here. That didn't work. I'm going to jump there. That didn't work. So if you jump too far, you'll never get good sampling. Is too narrow. If this is too narrow, you've got a sample here, you move to here, 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 and you're random walking around. This is literally a random walk. It's a biased random walk. So you random walk like this, but your posterior is the size of this room, then you've made a mistake. And if little q of theta, meaning the thing you're trying to sample is highly featured. For instance, theta space. If there's an island here, and an island here, and an island here, that's hard to sample, because it's very hard for samples here to jump to here, or to random walk over to here. Yes, you can also have things where, like the high posterior region looks like that, and it's very hard to random walk like that, it turns out. It still works. All of these cases will work if you do the right proposal distributions, but in general, it gets hard in these cases. These, by the way, are also cases where it's hard to be a frequentist. Because as a frequentist, say you're trying to optimize your likelihood function has 3 peaks like this. That's a little hard to optimize. In fact, there's proofs that you can't, in general, find the optimum of an arbitrary function without searching every single point in the function space. The no free lunch theorems. So MCMC is always hard at exactly the same time that any kind of inference is hard. Yes?
I was kind of taught one way to deal with this when you have a lot of random walkers with random initial coordinates, and then you could, that would be so it would avoid getting trapped in that position.
Yeah, I'm going to talk about that in a second. There's issues about, there's a set of issues for using MCMC, which I'm more or less just going to write down as a laundry list for people to think about. But we go through all of the issues in this 1710 archive paper. We go through the laundry list of issues and address them. So it's a place to go once you key off the things I'm about to say. Okay, good. Okay, good. So now, there are a million things to say at this point, but these samplings, when they work well, are unbelievably valuable. When you have a good sampling, when you can do these integrals, I should come back to here. When we do these integrals, these samplings are extremely valuable because, for instance, in the theta space, the scatter plot of the sampling is like an image of your posterior PDF. Or a histogram, if I now drop this down and plot the histogram like this of the sampling, this is the marginalization of the probability distribution down to one axis. The histogram on this axis is the marginal integral of that distribution, which you can just see. So like the posterior, the sampling you get out visualizes your posterior, and you can trivially visualize any projection of it by just plotting the projection of it. This projection of the sampling is the sampling of the projection. You know what I mean? If you project the sampling, you get a sampling of the projection. Because the samplings do integrals, and the projection of this space down here is an integral of the posterior, and samplings are for doing integrals of posteriors. So just projecting the samples is the same as sampling the projection. And that's the sense in which they're very just flexible, useful things, these samplings. They're very easy to visualize. Now the communities that use them have gotten used to looking at them. So if you can basically show your sampling and it sort of shows your results. Lots of good properties of samplings. But good samplings are hard to get. And the reasons are several. So what are the hard things about doing MCMC? The first thing is this Q is too wide, Q is too narrow. There is a problem called tuning Q of theta prime given theta t. You need to tune this function to make it work well. And as I mentioned, I am a co-author on a method called MC. And that method is a method that doesn't require tuning. But it's also got limitations. It has some limitations, but one of its benefits is you don't have to tune it. But if you're not using a method that automatically tunes itself, you will spend time tuning your method so it works. Another big issue, which was implicitly mentioned, is initialization. if you go back to this example here, if I initialize my sampler over here, it will probably get locked into that mode. If I initialize it over here, it'll probably get locked into that mode. And so your results can be initialization, both tuning dependent and initialization dependent. And this is a non-trivial thing, figuring out how to initialize. And actually, a lot of the frequentist inference that I do in my work is to initialize MCMC. Because often you want to do a kind of frequentist operation to initialize your MCMC. And of course, there's the point that was just raised, which is multiple initializations. And this is really necessary because you have to do multiple initializations to convince yourself that initialization isn't causing you trouble. So in fact, whenever you run MCMC, you always end up running it dozens of times because you run it with different initializations, you run it with different proposal distributions, and also and compare all the results. You'd end up running it a lot, which is nice that it's such a simple thing. There are much more complicated methods. I'm going to talk about other methods in a second. Next issue is that you have to judge what's called convergence, which really means the quality of the sample. You have to judge whether your sampling is good. And it turns out that there's no absolutely surefire way to tell that your sampling is good. There's nothing. So the funny thing is, the method is proven to give correct answers in the limit of infinite time, but there's no proofs about what constitutes infinite time. So that's a problem, and this is a limitation of using MCMC, is that you will end up spending a lot of your time thinking about this. And what we recommend here is due diligence, because we do not believe that you have to violate the rules of mathematics to have a publishable scientific result. This is similar to optimization. Often when we do optimizations, people ask, are you sure that you're at the global optimum of the function? And we say, there are theorems that you cannot know that you're at the global optimum, and therefore we think it's an unreasonable request from the referee that we be able to know. Good. So there's many convergence statistics, including Gelman-Rubin, and that is the kind of industry standard is Gelman-Rubin. We actually rarely use it. We use more heuristic things, but it is a good statistic, and it was designed to ask the question, are you good enough to doing reliable science? So I try to change this not to the question of absolutely are we converged, but change it to the question, are our results reliable from the point of view of a reasonable investigator? And that's true for optimization problems too. If you're optimizing a function, you will never know for sure that you're at the true optimum, unless it's convex, unless it's provably convex. But if you have a function that isn't, you're not sure whether it's convex, you'll never really know whether you're at the optimum. And you can't know. And somehow science proceeds. And it's because science proceeds through things we can do. We're doing the best we can, given the constraints of mathematics. So convergence of MCMC is in a similar category. And then there's another thing which I think is unbelievably important, and we really haven't talked about, and that is visualization. Almost all the times we discover there's something wrong with our MCMC, it's not really because of quantitative checks here. It's because of qualitative checks. We look at what happened in the sampling. And looking at what happened in the sampling is very, very informative, and you get used to it. Basically, if your sampling looks like a random walk, it's good, and if it doesn't look like a random walk, it's bad. So for instance, in a parameter space, let's look at one of my parameters. Let's call it theta 1. and this is versus time, because we're sampling. If it looks like this, then you probably don't have a good sampling. Because there's clearly two modes in your problem, and it only crossed between the modes once. It should look like this. Cross the two modes many times. You still have your two modes, but you've gone between them many times. That's more likely to be a converged sampling than that. We have such things. If theta 1, yeah, what you usually do is you fill, yeah, I mean, they look beautiful when you get weird plots. But in general, whatever you have here, there should be multiple traversals of whatever your range is here in your sampling. Many traversals, really. Even this number wouldn't be enough. You'd still want to run that 20 times as long. But this sampling would also fail the Gelman-Rubin statistics dramatically. But also, you could see from this, you would get ideas that you probably tuned it incorrectly, because you're somehow taking steps that are too small here, maybe. Or maybe you want to use a function here that kind of knows that you sometimes have to take big steps to force it to take some bigger steps. Things like that. You often learn things from your visualization. Also, from your visualization, you'll learn, well, I better initialize it near these two different optima. So you learn things about tuning and initialization and convergence by making visualizations of how the sampling went. And the sampling is technically a biased random walk, so it has the properties that random walks have, like the stochastic convergence and they should not look informative. They shouldn't look like they have slopes and things. They should look uninformative. Oh yeah, I'm not allowed to let you go before doing a very quick tour of methods. So if you ever start working on MCMC and start working on a problem with MCMC, you'll immediately be flooded by all sorts of people around you telling, oh, you should use this method. Oh, you should use that method. Oh, that looks like a Gibbs sampling problem. Oh, you should use nested sampling. Oh, try this importance sampler. Slice sampling works really well in these problems. People will throw all these like names of sampling methods at you, and you'll be like, I'm just trying to tune my thing here. There are a few small pieces of advice. So the first thing I would say is this is Metropolis Hastings. This method here is called Metropolis Hastings. Or actually, this is called Metropolis, I think, strictly. But anyway, this kind of sampler is actually, for small problems, will actually often just solve your problem. So we encourage people to code up this before they try anything else. And you usually learn a lot by coding it up. You learn a lot about initialization and tuning. You learn how hard is my problem. And sometimes it just solves your problem, and then you're done. And then you have the pride of having made your own sampler. So we strongly encourage that. And then we suggest you only go on to more advanced systems if you really need them. And let me give you a little rundown. Okay, so as you know, I am a co-author on MC. MC is an ensemble sampler, which means it's not moving forward just one point in the data space, in the parameter space. It's moving forward a cloud of those points and uses the properties of the cloud as the state of the sampler instead of the property of any one sampler. So this is very good because it doesn't need to be tuned. So if tuning is killing you, this thing can help you because it doesn't need tuning. But it only works in small numbers of dimensions. It does not work for like 40 dimensions. So this should be dimensions like 12, but not like 1200. Okay, so that's one thing I would say. The next thing I would say is, no, it literally just takes forever to converge. So we've done problems with this where we try to compute the volume, very trivial problems, like use it to compute the volume of a cube in 1,000 dimensions. And it basically just takes forever. And we don't fully understand why, but there is a lot of literature on comparing different methods. So if you want to go to large numbers of dimensions, more and more people, back when I was a kid, we never even thought about doing inference with more than like 6 or 7 parameters. Like, what are you, crazy? And so this method was built largely in thinking about problems of that scale. Now we regularly have problems where we have problems where we have 150,000 parameters. And we would never have considered such problems 10 years ago. Now people want to even sample them. So if you're going up to large numbers of dimensions, to my knowledge, the only options are HMC, which doesn't have like a best reference implementation. This is called, the H here is for Hamiltonian. This treats your problem like a dynamical problem, like a dynamical system, and uses dynamics to speed the sampling. So what it does is the samples like fly around the space on orbits with stochastic kicks. And so you're stochastically kicking. It still requires tuning, but it works in much higher dimensions. So you do have to tune here, but you can deal with large dimensions. And people have done problems with hundreds or thousands of dimensions in HMC where we're very confident they are converging. And then there's problems that have been done at hundreds of thousands of dimensions which probably aren't converged, but at least it doesn't bork. It does something. Yes?
So in that case, is your likelihood, I mean, if you can construct the likelihood with that many dimensions, is it something like a product over stars or something like that?
I'm going to come to that thought in a second. So this is generic. HMC is generic, will work with any form of the likelihood function, but it has a requirement. So this is like what's good, what's bad. Okay, so this is like yay, it's good, this works in large dimensions, but the bad thing about HMC is you need derivatives. Need derivatives. Because as you may recall, forces are gradients of potentials. So, and remember, this is a Hamiltonian method, so it's flying your point around your space, so it actually needs to know the force law, and the force law is the derivatives. So you need to write code that has its own derivatives. If you numerically calculate, you lose all the speed advantage. You have to have analytic derivatives. But one thing everyone in this room should know is now many computer languages support auto differentiation, which means when you write your code, you just run a post-compiler or a pre-compiler on it, and it produces code that analytically has your derivatives. I don't know whether people have seen that. That's built into TensorFlow. There's NumPy decorators so that NumPy code can do this. There's basically, we are headed into a world where you will always have analytic derivatives and you never wrote them yourself. And the reason is that chain rule can be applied by robots. So since you can write a piece of code, you can write the chain rule that applies to that piece of code. And so you can automatically generate the derivatives of your code. So one of the many reasons HMC is taking off as a method right now is that HMC is capitalizing on the fact that everyone has analytic derivatives now. Not everybody, but if you don't have analytic derivatives, you should. If you're writing a simulation or something right now, write it in a language where you can just turn on the differentiation, and then you'll find you get the whole derivative of your simulation with respect to the initial conditions, or with respect to the control parameters. Good. The other way to go large is to capitalize on problem structure. So there's a structure called Gibbs samplers, which capitalize on, remember I drew that graphical model with the box? Remember the graphical model I drew with a box? That box means there were a set of repeated objects that were all independent. If you have a set of repeated objects that are all independent, Gibbs allows you to send those out to the data center, sample them independently, and bring them back. And so you can actually do a sampling that is as large as your data center in principle with Gibbs. In practice, very few people have succeeded. But Gibbs can do large. maybe even very large, because it's distributed in a certain sense. But you need hierarchical structure. And I'm not going to fully define that, but what I mean is that there's shared parameters, and then there's you can cut the problem into independent chunks and sample parts of the problem independently. And then there's many more methods. There's infinite numbers of methods, and there's books. There's whole large textbooks on different methods. In our world, one that comes up a lot, I'm going to just raise this, I'll put it back down in a second, is nested. Nested sampling, and there's various different kinds of nested sampling, and I've actually been an author on some nested sampling codes. These have the advantage that you get your sampling and Z. You get your sampling and you get Z. And they're also designed to be good on multimodal problems. Problems where there are multiple modes. These are kind of designed to find those modes. So nested sampling is very, very interesting here, but it is very hard to use in practice. This is hard to use, and it's hard to get converged samplings. So I consider this sort of the most difficult method. And so I generally don't recommend using nested sampling unless you really need to know capital Z. And I avoid ever needing to know capital Z. So I basically don't use nested sampling very much, but I have contributed to some nested sampling problems. Most of my problems have Gibbs structure. So we often imagine we're going to use Gibbs, but then we turn on auto-differentiation and HMC solves our problems anyway. So almost all of my work is here right now, MC and HMC. Yes?
So what would you recommend for multimodal distributions instead of nested?
Well, I would recommend nested sampling for multimodal distributions, but it's not obvious to me at the end of the day that the nested sampling is getting all the modes either. So nested sampling, the people who believe in nested sampling would tell you that it will get all the modes, but actually demonstrating that it gets all the modes is very hard to do. It comes into the same category as discrete optimization, like there's no free lunch. So you can't really know that you're getting all the modes, whatever you do. So the problem of sampling multimodal distributions is an unsolved problem. There's no currently best solution. Well, one thing to do is sometimes you can use search, like grid search or pure thought, to figure out where the modes are going to be, and then do isolated samplings at the modes. And we sometimes do that. We actually have a project. We have a sampler called the Yoker, which I won't explain why, where we literally densely sample the entire parameter space and evaluate the likelihood at every single point in the parameter space, which is the most idiotic thing you could possibly do. But that is safe. So sometimes you have situations where you need to be safe. Sometimes you have situations where you need performance. If you're willing to spend the computation, the safest thing to do is to sample the prior and then evaluate the likelihood function at every prior sample. That's allowed. But my God, you'll pay for it. We've used a very large fraction of the compute resources in New York City doing that. Yes?
What is the typical dimension of the parameter that you work on the nested?
For MC? Oh, for nested. I don't really know. We do think we did do some tests of nested versus MC for some simple basic problems like computing volumes of things. And nested did look like it went to higher dimensions better. But I still don't think nested sampling can go to the kinds of dimensions that HMC can go to. It's still inside nested sampling, you're still doing some simple MCM, metropolis-like sampling. It's just you do it in these, in different versions of the problem. So you basically, in nested sampling, you take your problem and you turn it into a set of nested problems that are of increasing difficulty. And you sample the easiest one first, and then use the easy sampling to sample the next easiest, and then eventually get a sampling of your true problem. And in that sense, there's another set of methods called tempering, which I don't think they're not, for my uses, they haven't been as useful, but that's also a similar thing where you try to sample an easier problem and use the easier problem to help you sample the harder problem. But I think if you're getting, once you're getting, by the way, at 12 dimensions is where most computer scientists would tell you you can't do density estimation anymore. So, people want density estimates. If you have 100-dimensional data, you cannot estimate the density of your data in that 100-dimensional space. It just doesn't work. There's no real method for doing it. And so MC kind of fails where density estimation fails, and I think basically so does nested. And so the beautiful thing about HMC is it seems to be able to get through that barrier and work in places where density estimation doesn't work. We don't really understand why. There is some theory. Yeah, we're out. We're out. Let's take last questions at the end.
Can you compare how well these methods paralyze?
Only Gibbs paralyzes well. That's my current belief. Yeah, one of the things that's terrible about being a Bayesian is it's hard to work in the data center. The only problems that really parallelize like that are optimization problems and Gibbs sampling. You have to have problem structure to capitalize on. We're out of time. We're taking last questions up here. Oh, yeah. In fact, you're going to always run, whatever you do, you're going to run it multiple times. So there's kind of a trivial parallelization where you just send it out into the data center, lots of different operations. But yeah. But not in a single run. Okay, good. We're done. We're going to crowdsource the next 2 lectures. So get your votes in or